CHEM152. This is chapter 11, the last chapter before the next exam. So if you take a look at the homework, there's 2 assignments out there that are due on the 28th. I really encourage you to come to office hours. There's been a lot of new material, and then also exam 2 is returned. So if you want to go over what happened on exam 2, what went well, what needs to improve on, remember the final is cumulative, so you need to retain this information. So definitely come see me in Zoom. It could also help prepare you for what's coming up, Quiz 5 and Exam 3. Please note the review sheet is posted for Exam 3. And if you're considering withdrawing, let me know. We can talk about it if you want. So we have 1 chapter now left before the exam, and it focuses on gases. And last chapter, there was a lot going on, a lot of conceptual. How do you draw Lewis structures? What are the shapes? Is it polar? Is it not polar? It's really dense, a lot of information. This chapter is going to be fairly short. That doesn't mean there's not a lot here, but fairly short and a lot of quantitative work. Okay, so if you've got the calculations, if you've got the equations down, this I think is a very different chapter than chapter 10. So what's remaining? Chapter 11, Quiz 5, then Exam 3. And then we start up again, and if you'll take a note here, we are skipping chapter 12, and we'll come back to chapter 12 at a later time. So we're focusing this whole chapter on the state of gases. Okay, so let me make a note here. There was clearly an error here. This is 2020. What we're going to do is talk about the theory of gases, the equations, and then how that ties into other equations that you've already done. So what we're going to see is there is an ideal gas law, okay? And this book does it kind of uniquely. It presents you the ideal gas law. It says, here it is. A lot of other books talk about the individual laws first. So there's Boyle's, Charles, Avogadro's, there's a couple of others. Those laws are talked about first, and that leads up to the ideal gas, but we're showing in this textbook the ideal. Okay, so maybe you've seen this before. Most likely you probably have seen it written like this: PV equals nRT. This is the ideal gas law. If you have a lab at Miramar, one experiment will go 100% on the ideal gas law, and you'll solve for R, which is a constant. Okay, so remember, you get constants. This will be provided to you. What I really want to emphasize is that if you see units, that's giving you a lot of information. Okay, that tells you liters, volume, atmosphere, pressure. Those go on the same side. And then on the opposite side are the temperature, and N stands for moles. Okay, so this is the ideal gas law, PV equals nRT. So remember, 0.0821 liters atmospheres per K per mole, that will be provided. So if you get a problem like this, what you should be thinking is, I've got moles, and I've got pressure, and I've got temperature. Okay, so what about the volume? That's a PV equals nRT problem. So you can go ahead, pause this and set this up if you want. And remember, the constant is 0.0821 liters atmospheres mole K. So with this problem, it's very straightforward because everything was given in the correct unit. So there's moles, that cancels. Kelvin was given, Kelvin, that cancels. Atmospheres, remember the constants in atmospheres. The answer wanted to be in liters, and here it is in liters. So you know the equation, multiply these 3, divide by 1, you get that one, okay? So this reminds me of Q equals MC delta T. You had to know the equation, but remember, you also had to know what each thing stood for. Q was heat, C was the specific heat capacity. So we're going to go over these terms. How do we get to the correct units? We're going to go over pressure, what pressure is. So we'll review this, but this is a good start to PV equals nRT. So let's talk about gases. The unique thing about gases for sure is they're really independent of its identity. So whether you're talking about hydrogen gas, oxygen gas, these gas laws apply to all of them. Okay, so that's very different than solids or liquids. Those stand out significantly. So the gas law are going to be explanations for this theory is going to be the explanations for these equations that work. Okay, so why do these equations work? The theory is going to explain this. And this is called the kinetic molecular theory. Okay, so it's simple, but it's very successful. And please note, it works in normal conditions. In Chem 200, we talk a little bit more detail about abnormal conditions. I'll just go over one slide on that in this class. So there's 4 things that we're going to see in this kinetic molecular theory. 4 statements that are important for understanding the concepts. So the equations are going to be very quantitative. You're going to plug in the numbers, get answers, no problem. But this really will stand out as well. Why? What's the theory? So what's the explanation for this? All right, first thing, the particles are moving in constant straight line motion. Okay, so very active, high kinetic energy. They're moving so fast and they're so far away from each other that they don't attract one another. Okay, they're separated from each other. When they do collide, whether that's with other particles or the walls, they don't lose energy. They just bounce off like billiard balls. Mostly empty space. Okay, so a lot of empty space between particles. That goes back to, again, why they're not attracted to each other, because they're so far away from each other. And I mentioned kinetic energy earlier. So the kinetic energy is proportional to the Kelvin temperature. This is really key. We have to be in the Kelvin scale when we talk about this, but you go up in temperature, you go up in energy. So particles move faster when they're heated up. When you cool them down, they slow down. All right, so what does this mean? This is what predicts, okay? So compressibility. Gases can be compressed because the theory says, oh, there's all that empty space. So all that empty space can be minimized by compressing gases. So that's compressibility. And the gases fill the container, fill the shape of the container, fill the volume of the container, because they're moving around constantly. So the gas particles aren't going to settle at the bottom of the jar. They're going to fill the whole thing up because they're constantly moving around. So I've already mentioned this idea of pressure, and I'm sure all of us can say, you know, we understand pressure. We've felt pressure before. Well, what does that feel like? You know, usually for me, like it's my shoulders, right? Just something, it just feels like it's pushing down on me, like there's so much tension, pressure. Well, that's the definition, okay? Pressure is the force, so pushing down, force over an area, okay? That's the definition of pressure. So there's several units, and maybe you use pressure, maybe you're familiar with pressure, maybe a sports ball or a tire. So you might be familiar. I'm going to tell you what we're going to use, what the units for pressure we'll use, but then I'll also point out some others. So a couple of things. Where does this gas pressure come from? Okay, so it's a cumulative force, so it adds up of all these collisions, okay? And the collisions are between the particles, the walls, all of this. So I want to point out a couple of things here. First, this low pressure, you can see there's less number of particles, so there's less collisions with the walls, less collisions with each other, okay? Here, if we increase the pressure, then you can see there's less empty space, more collisions with the walls, more collisions with each other. So you could also think about pressure in terms of amount. Okay, if you have a low pressure, there's not many particles present. Okay, a higher pressure has more particles. Okay, so that's low pressure, high pressure. It makes me so sad to show this slide, but you've probably experienced this. If you've flown on the plane and you've had a terrible pain in your ears, you've understood the difference between a pressure imbalance. Okay, so here you can think about a higher pressure, and a higher pressure means there's more particles, and then outside is the lower pressure. So this is a pressure imbalance. You've got this force pushing up, and it's painful. Children, babies are crying. I think I've wanted to cry for sure when I was sick and I had this pressure imbalance. So this is what happens when we're talking about a difference in pressure on in the ear. So another way to look at this is thinking about atmospheric pressure, and it's very common to see mercury used to measure pressure, and mercury is really dense, so that's why it's used, because then the height that this mercury is going to go up is going to be a lot less than if other substances. If it was water, I think it's like 3 meters high that water would go up, okay? So that's why mercury is used. Well, it's also toxic, so you don't see things like this anymore where just an open dish of mercury. But if we were in the lab and we were looking at the barometer on the wall, it is filled with mercury for this reason. So if you can look and see that the particles in the air are pushing down on this bowl here of mercury. This tube was evacuated. Okay, so there's nothing in here. There's no gas particles, there's no water vapor, there's nothing. It's empty. So then the mercury, because this is being pushed down, the mercury gets pushed up, and you can see here, this is a measure of distance, 760 millimeters, or 29.92 inches. Okay, that's a measure of distance. You've used your ruler, you've measured inches, millimeters, that's what that is, and that's measuring the atmospheric pressure by measuring the height of that mercury. So that's the pressure of the atmosphere, and that's the atmosphere pulled down by gravity. Okay, so barometers I mentioned would be in the lab that you could see if we're in the lab. That measures the change. If you look at your weather app, it'll also show INHG. That's the pressure, and can be real careful. That's the pressure in inches of mercury, INHG, not in mercury. So that's inches of mercury. And this was invented in 1643, this device to measure this. So you can see in some places torr is a measurement of pressure, and that's in honor of Torricelli. So let's talk about some units then of pressure. We just saw millimeters of mercury. That's really common to use. This is Newton per meter squared. That's Pascal. Well, this is what we're actually going to use, okay? We'll use 1 atmosphere, 760 millimeters of mercury, and I already mentioned the torr earlier. You can see the torr and the millimeter of mercury are the same. That's the same number, just the unit is written differently. So those are the ones that we'll use. 1 atmosphere, 760 millimeters of mercury. That's what you'll need to know. So this one's available, kilopascals. I just wanted you to be aware of it. Those that, you air up your tires, you're probably familiar with pounds per square inch. So 32 or 30 psi, whatever your tires are, that psi is pounds per square inch. So that's an English unit, but these are the two units we'll be using in this chapter. All right, so go ahead and then convert. Again, you need to know one conversion. 1 atmosphere equals 760 millimeters of mercury, and that's torr or millimeters of mercury. So convert torr to atmospheres or atmospheres to millimeters of mercury. Dimensional analysis, remember, setting up, torr, 575 divided by 760, sig figs. This is 3 sig figs. This is exact, so you get 0.7573 sig figs. Atmospheres cancel, and you get 3 sig figs, 1650 millimeters of mercury. So let's take a look at some of the gas laws then. We can see here we're talking about pressure, temperature, volume, and moles. Remember, ideal gas law is PV equals nRT. So we want to know those variables. We want to know the units of R, how that uses to help us. So that's important to be aware of. So what happens in gas equations generally is you're given 3 variables and calculate the 4th. So you could rearrange, solve for volume, you could rearrange, solve for pressure, solve for any of these, but you need to know PV equals nRT and then rearrange. So now we'll talk about how some of these laws contributed to the ideal gas law to get this equation. So the first was Boyle's law, and this is a pressure volume. So pressure volume relationship from PV equals nRT. You can see it's an inverse relationship. That means if you go up in pressure, you go down in volume. Okay, so if we look over here, the gas volume is here. And then if we add more mercury to this, okay, so that's more pressure, then the volume decreases. So increased pressure, decreased volume, that's the law here. So I really encourage you, you need to be able to do calculations, but it's also important to think about conceptual. If I increase pressure, what happens to the volume of the gas if we're only changing these two variables? Okay, so this is assuming the moles of the gas are constant, temperature are constant, so it's just pressure, volume. So this is showing that volume and pressure are proportional inversely, 1 over, so that's what we're showing earlier, P times V, that equals a constant. That's what we say here to see this relationship, okay? So remember, if you've got two variables, then you've got two things that are constant at constant temperature and constant moles. So that's called Boyle's law, pressure, volume. And you can see here again, the weight is representing pressure. So that's small weight. This is a much bigger weight. So you can see 1 atmosphere, 2 atmosphere. And then of course the volume changes from 1 to 0.5. So here we could do the calculation, PV. So if it's constant, then we can set up an equation that they're the same. Because remember, the moles, the amount, the moles, and the temperature are constant, so pressure, volume are the only things that are changing. The next one is Charles' law. That's volume and temperature. You can see here, volume, temperature. So remember, if we increase the temperature, there's going to be more kinetic energy. So that's going to need to take up more space, okay? Increased temperature, increased volume. So these are proportional to each other. And if we look here, this is a nice linear relationship. So this is PV equals nRT. So those are proportional to each other. And if that's V equals T, then I can rearrange this that they equal a constant, and you can set them equal to each other. So this is V2 over T2. Okay, so that's our Charles' law. And you can see here, you can measure these, and then what's happening here is it's extrapolating all the way back to this theoretical temperature of where the particles would stop moving. That's the absolute zero, that's 0 Kelvin, or minus 273 C. So that's the absolute zero, that's the extrapolation. Again, they just graphed some points and then took it back to get there. So this isn't measurable, you can't get down to this, but that's known as absolute zero. So this is where that conversion comes from of how to convert Kelvin and Celsius. It's at 273. So Celsius plus 273 gets you Kelvin. So absolute 0 Kelvin is minus 273 Celsius plus 273, that gives you your 0 there. And please note, you can see here, this is degrees Celsius, but because this is the absolute scale, there's no degree to this. So that's Charles' law. Remember we said that's directly proportional, so that's that V over T is a constant. And here, a good example of this, and you can actually, there's a nice video, if you Google or YouTube, balloon animals and liquid nitrogen, that will show this way better than this, but it puts balloon animals and liquid nitrogen, which is really, really cold, and all the balloon animals fit in a very small space. And then you take the balloon animals out, and it warms up, gets to a much bigger space. So this is volume and temperature, Charles' law. So we've done pressure, volume, temperature. Well, that's 3 things that we can put all those together. So I've been writing equations. Now you can see an equation that has all 3 of those in there. So pressure times volume over temperature equals pressure volume over temperature. So this leaves out one variable, and that's the amount or the moles of gas. So this is saying if moles are constant, moles on the left, moles on the right are the same, then you can set this up PV over T, PV over T. So go ahead and take a look at this question here. Again, we've gone over several equations just really quickly. So you want to sort out and figure out what you've got. What are my variables? What equation do I need? Do I need to make any calculations? So go ahead and go for it. So you can see here, you're given volume, you're given millimeters of mercury. You need to know what's millimeters of mercury, that's pressure, and you're given temperature. And I really want to emphasize, anytime you're in temperature and gases, you have to go to Kelvin right away. Okay, so then you're also given another volume, that's milliliters, and you're given another temperature. Right away, you got to go to Kelvin when you're doing these calculations. So it says, what's the final pressure in millimeters of mercury? Well, you're in millimeters of mercury, and you've got pressure, volume, temperature. You've got temperature, volume. You're looking for pressure. So guess what? We've got our equation then. That's pressure, volume, temperature equals pressure, volume, temperature. Well, take a look here. There's no constant, there's no R in this equation, like the ideal gas law. Remember, PV equals nRT. So if we have PV equals nRT equation, we're using R, and remember I stressed that R has a specific set of units, okay? Here, there's no R, so guess what? You can use any units you want except for temperature. Temperature, gotta be in Kelvin, and then you can take a look. You can put this in millimeters of mercury. You can put this in milliliters. The key is you just have to do the other in the same. So milliliters over milliliters, those cancel. You're left with millimeters of mercury. That's the answer with the correct unit. So it's important to know, when do I need to convert, when do I not need to convert. If you're using R, you have to convert to liters, atmospheres, moles, Kelvin. All right, so let's take a look at another equation. We've got a movable piston, we've got this ATM, we've got this L, and we've got this ATM. So you've got to recognize right away that this is pressure. This is pressure, and this is volume. Okay, so we only have two variables in this case. So we need to think about what equations we're going to use. Well, if you go back to the ideal gas law, you're looking and saying, wait a minute, pressure, volume are on the same side. Moles, temperature, I don't have moles and temperature, so we're not using this equation. But if you take a look, all of this is constant. So I'm just putting this down as a constant. So then if we have two conditions, we can say P1, V1 is equal to a constant. Well, and that constant is the same value when you take P2 and you multiply it by V2. So now you've got your equation from the ideal gas law after you figure out what's constant. And if you take a look at here, you've got the units. Pressure is atmospheres, volume liters, divide by pressure, and you get the volume. So there's a lot of ways you can be asked. The main thing is, what are the units of your four variables? What equation are you going to use? Set it up and solve. So the last step to get to the ideal gas law from the combined was the PV over T, is looking at moles. That's the very last one. And we can look and see that this is another gas law that's needed. Okay, Boyle's pressure volume, Charles volume temperature, the combined PV and T. Now we need one that has moles. This is Avogadro's law. This is moles. The more moles you have, the more volume you need for constant pressure and temperature. Okay, so you can see a nice linear relationship. That again is this directly proportional. So again, you go back to PV equals nRT. If they're on opposite sides of the equals, they're directly proportional. So you increase volume, then you increase moles, then you increase volume. Directly proportional. Good example, blow up a balloon. You can imagine you put in air in the balloon, it has a certain volume. You put in even more air of the balloon, the volume's going to increase. It's not going to decrease unless it gets let out, but this is adding more volume by adding more moles. So those are our equations, okay? So if we're doing an ideal gas law, it's probably good to visit and say, what is an ideal? What does it make ideal, okay? So this works when gases are acting ideally, okay? This perfect idea, this perfect world. Well, what does this mean for gases? The volume of the gas particles must be small, and the forces between the gas particles are not significant, okay? So this is the one slide that I'm going to go to for the ideal, non-ideal. Again, come to Chem 200, we'll talk a little bit more detail about this. So this low temperature, high pressure is going to stand out for non-ideal. So I'll talk about that here. What we're seeing is, remember this, gases, mostly empty space, and you can see they're going to have collisions, but they're very spread out. Okay, so this is high temperature, which means they're going really, really fast. They're not interacting with each other. They're moving really, really fast and having collisions. Low pressure, so there's not much amount in there, and because there's so few, there's not much collisions with the wall. So if you take a look, this size of these particles takes up very little of the whole container. Okay, that's very small comparison to all this empty space. So particle size is small, and because they're moving really fast, they do not interact with each other, so that's insignificant. Now here's non-ideal. Okay, non-ideal, things are slowing down. You see this is low temperature and high pressure. High pressure, remember, look at all the amount. Now there's not as much empty space. Look at all this empty space. There's no particles. That's all empty space. And here, not as much, for sure. So you can't even avoid all of these because there's particles everywhere, okay? So empty space. So particle size is significant. It's taking up a lot of the space of this container. Because there's not much empty space, now these particles are interacting with each other. This is going to make it non-ideal. Okay, so this is the difference between an ideal gas and a non-ideal gas. So one thing we're going to add, and this is actually seen in the lab at Miramar, is when you have a mixture. Okay, so this is not one independent ideal gas, but it's a mixture. It's a combination, a physical combination of these gases. So just like air in the room that you're in is a mixture of nitrogen and oxygen and other gases, this is looking at a mixture. And each mixture, there's a partial pressure. Okay, so there's a certain amount of hydrogen, or there's a certain amount of oxygen. So clearly there's got to be a certain amount of oxygen in your room, or that'd be a problem. So that's a partial pressure of oxygen. Mostly in your room is nitrogen. So the partial pressure of nitrogen is much higher than oxygen. But the law, these are just additive. Okay, so whatever the pressure is of nitrogen, put it in the same units as oxygen, add them together, put it in the same units as CO2, add them together, and you can calculate whatever gases you're in the room that you've collected, that contributes to the total. Okay. So how this is going to work in lab is you're collecting a reaction that forms hydrogen gas, and you're doing it over water. So that actually creates water gas or water vapor and the hydrogen gas. Okay, so you have two gases, so that's a mixture. Well, that's no problem. We just said a mixture is just additive. You just have to have them in the same units, and that equals the total. Okay. So the partial pressures of water are tabulated, and it's called vapor pressures. So you can look this up in your lab book and find the vapor pressure of water at a certain temperature. And then in lab, you're going to look up and you're trying to calculate this pressure of the gas. Well, no problem, because you're going to measure the gas pressure of the atmosphere. Okay, and I'll talk in lab why that's done that way. So you can solve for the pressure of hydrogen gas. So let me show you what's going to look similar to in lab. At Miramar, we actually do this with magnesium. So you put in magnesium, hydrochloric acid, and the gas bubbles out of this tube. This is sealed, so the gas goes under the water and it bubbles up into this container into the gas molecules. Okay, because this is over water, you see this is the surface of liquid water. Well, water also can go up into the gas phase, so you can see we've got to account for this, and we do that by that equation. So that's the atmospheric pressure equals the pressure of the hydrogen plus the pressure of the water. So you measure the temperature of the water and you get this value. You measure the atmospheric pressure from the barometer on the wall and you get this value, and then you can subtract and get the pressure of hydrogen. So here's an example, temperatures, and actually your lab packet has a lot more precise temperature readings, and then the water pressure here in millimeters of mercury. So we've been talking a lot about gases, and we're going to do all this work on gases, and then it takes us back to stoichiometry. Okay, so that's this idea that, wait a minute, grams, moles, particles. That's the roadmap that we talked about. And then we got to even more complicated, and we said, well, we can convert through chemical equations moles to something else, mole ratio. So we had this roadmap, grams, moles, particles. But guess what? We've been talking a lot about moles in this chapter. So this piece right here, that's where we can get back into this, is with our variables. Pressure, volume, moles, temperature. Those are our gas variables. That takes us back into the mole stoichiometry. So we're going to do some equations with that. But the gas can show up as a product, it can show up as a reactant. So however it is, it's just back to stoichiometry. It's moles of whatever gas you have to convert to moles of something else. So if we're going moles to mole, that's mole ratio, that's the mole relationship. So now we can just use ideal gas to get us there. One thing I do want to point out is we're going to talk about STP. That's called standard temperature and pressure. So temperature, 0 degrees Celsius or 273 K. That's standard temperature. Standard pressure is 1 atmosphere or 760 millimeters of mercury. So that's standard temperature and pressure. And remember, these are ideal gases we're talking about. So if these gases have the same temperature, same pressure, 1 mole of those gases, doesn't matter what gas you have, is going to equal 22.4 liters. So you can check that if you want. You can put these numbers in, PV equals nRT, and you should get 22.4 liters. So if you've got this relationship, remember this relationship is only for gases and it's only at STP. So if you have 1 mole equals 22.4 liters and you have ideal gas law, you're going to do stoichiometry with gases. You're good to go. You're all set. Okay, so let's take a look at this equation. How many liters of oxygen? We haven't done liters from balanced chemical equation, so that should be telling us right away that's an ideal gas law equation. So how many liters, PV equals nRT, when we've got 294 grams, completely react in this equation. So if you think about your roadmap, we've got grams of this to moles of potassium chlorate, and you got moles of potassium chlorate, no problem. You can go to moles of oxygen, you got moles of oxygen, you can go up here, PV equals nRT, because you're given pressure and you're given temperature, so now you can solve for liters, okay? So I want to remind you, if you're given R, okay, 0.0821 liters atmosphere mole K, that should be a red flag that this has to be in atmospheres, This has to be in Kelvin, so that's okay, that's good. And you can't put in grams, so you've got to convert this to moles, and it's got to be converted to moles of the gas. Okay, so if you take a look, grams get you to moles, that's moles of potassium chlorate. This mole-mole ratio gets you moles of oxygen. If you've got moles of oxygen, then you go to PV equals nRT. So that's moles. This is your R, and if R is in atmospheres, then this pressure has to be in atmospheres. That's 0.993. Kelvin, the temperature was already in that, and then you put in the pressure. That should give you 90.7 liters. So recognizing gas laws, stoichiometry now involves cumulative things, right? Several things you've done, balanced chemical equation, mole-to-mole conversion, now the new piece, ideal gas law. Another question here, once you see the red flag, is STP. So right away, if you see STP, you should be thinking gas, 1 mole, 22.4 liters, okay? So if you have liters of hydrogen and it's asking for grams of water, the roadmap is 1 mole equals 22.4 liters. Mole-mole ratio doesn't change the value, but it changes the units. That's really key. And then molar mass goes to grams of water. So I encourage you to get started on the problems, homework for chapter 11, and come see me in office hours if you want to go over this.